right. And thank you all for having me. Stephen and the team, I don't know if I can see you, but thank you for the invite, and hope I can show a bit what we do in GSK, and especially in the supply chain space. So maybe for people that don't know GSK, and this global supply chain, the global supply chain is actually everything after R&D. So once things get filed, once things get into production, and when we want to ship things, vaccines or medicines to our patients, right? So as you can see, we have 37 sites around the world. We currently serve 1.4 billion patients a year, and we have ambitions by the end of 2031 to get that to 2.5 billion patients served per year, right? So we have massive growth ambitions, and we have massive reach with our medicine. And I think for everyone here in the audience that has children, probably your children got vaccinated by one of our products if they were born here in the UK. So the reach is big, and the impact is big. So first off, I wanted to talk a bit about how we look at agentic. People have been talking about agentic as well, so of course we are doing agentic supply chain as well, which is really about a new era of moving away from BI systems to much more autonomous systems, much more smart decision making, and much more working with your data rather than just reporting on your data. This is not as easy for us because we have a very, very complex decision network. As you might have heard before, maybe not aware of, making a vaccine or a medicine might take a year or so. So the lead times, the cycle times are very, very long, and every decision you make might put time on it or risk on it or maybe cost a lot of money. So it's not so easy to make a single decision in silo. You kind of have to always think through what this decision might mean, one step down or one step up, and how you actually keep reaching the patient in time with that product. So what we need to do is actually make sure that we integrate this whole complex decision network, understand all the different KPIs that all the business stakeholders have, and start really mapping them together and actually feeding them to these agentic systems in the right way, so that actually that you know if you make a decision somewhere, that you can simulate what the impact is. To put it in perspective, one of the scenarios that we're working on is really around having an assistant, right? So imagine you will be a brand manager for one of our products. Obviously, things can go wrong. Today, that will be observed by looking at BI dashboards. You see a KPI going red. The brand manager might need to make some calls to understand what's going on. The scenario we are working on today is really like getting an autonomous notification, like, hey, something is wrong, but at the same time, then start guiding this brand manager to the next steps, what he should be doing. So we're building agents that are doing root cause analysis, trying to understand, do we understand what's going on? We try to make agents that start predicting scenarios and say, like, what if we do this, what if we do that? What is the outcome, what is the impact? And all the time give these kind of more directive information to our end users, to the brand managers, so that they can take the decision because they are accountable. But from now on, they are much more doing that based on data rather than in the past where it was much more done on human knowledge. So it's a very complex system. To do that, we're building our own user interface. I heard already before today, user interfaces are dead. Well, we're still building one ourselves, and this is really to bring agents to everyone in the supply chain, where we focus very much on all the aspects that you need to make decisions, right? So we build in very advanced reasoning capabilities. We ground everything with our enterprise data, so we call it Code Orange, that's our Azure Lake, but also very much feeding all the common data models in there where all the KPIs are. We have a lot of supply chain knowledge in Viva, so we try to ingest that as well so that the agents can actually reach that. We work on dynamic libraries for illustration, but again, because we need to make sure what these illustrations are, we don't want to give all the freedom to the LLM to make up whatever illustration. Again, we kind of give it some sort of guidance, right? We try to prompt direct to make sure that the illustrations are fit for purpose. And we actually also, based on a lot of the experience we had with our end users, start putting much more guiding prompt instructions in it as well. So from our first iteration of building these tools, we noticed that a lot of end users really didn't know how to work with these systems. So we started to building more on like LLMs that actually help people, right? Next best steps to ask, what qualification to ask, updating the LLM. And then the last one, we build in continuous learning. That's what we do with Weave, where we trace everything that we do and make sure that we track if users are happy or unhappy. And we have a strategy for long-term and short-term memory, because that's the one thing we would like to crack as well, that if you always work on one brand on one side, that the next time you start the system, it actually knows that, right? And if you ask about your OTIF, you're on time in full, it actually knows you care only about one site and you don't care about the whole company. So to do that, we have built a framework in-house together with Microsoft, which we called IGA, and what it does is actually very simple, right? It takes a question from a supply chain persona. So in this case, someone is asking, what is my supply chain performance versus what the design performance should be? So just really trying to understand, is the OTIF on target, or is the cost of goods correct or not correct? The orchestrator will then try to find some background information on this question. So we would go into things like meeting notes or other types of memory to see if there is some information it should be aware of. It also goes to our SOPs. These are really our documents where we guide the procedures, so really to ground in GSK processes. Only after that he will make a plan. And he's saying, based on what I know from short-term memory, what I know from our processes, I might want to call these apps or these tools or these kind of planning, and I want to enrich it with this type of data sets. And only then he starts running the reasoning and give the answer back to the end user. And then the other thing, of course, that we built in, we wanted to build in tracing end-to-end, right? So every step is traced, logged, so that we can always go back and say, like, why were certain decisions made, or why were certain decisions suggested, so that we can, over time, fine-tune it and make it more fit for purpose. Doing that, we learned actually a lot of things, and I think many people in the room have the same experience, right? So evaluation is very difficult. It's no longer just making sure that the model does predict the right number. You actually have to compare text versus text, which is very, very hard. So we have to come up with new strategies of how to do that. We also have the constant risk of regression, right? There's constant new frameworks, there's constant new tooling. I mean, even today here, people talk about all this new kit. Often these things break things unintentional, so you need to really be good in testing your solutions. The other one is the black box for reasoning. Especially in the early days, everyone wanted just to reason, but without tracing, it's very hard to understand why a model gave a certain outcome, and we needed to invest much more in tracing. And the last one, there's always the ask, why don't we move to the next LLM? Right? There's always a new LLM that looks much better, so there's always the ask, why don't we go to GPT-5? Why don't we go to whatever new model comes out? So we need to be much better in actually comparing models with internal benchmarks, not with external benchmarks. The other thing that we noticed is we started this GPT stuff in 23, so we released already products when we were still using GPT 3.5. Over time, you have to actually get the structure of how you upgrade these LLMs, right? So this is very different than before. Before, often we trained a model, it hit an accuracy, then we froze the model, we went into production with it, and we never touched it again, right? If the model does what it needs to do, it's good. With LLMs, you don't have that luxurious position. LLMs come and go, and as people maybe know, like for example, GPT 4.0 is going to be removed very soon, right, in the next 12 months. So you have to really start thinking about, okay, how do I continuously test my solution if I want to upgrade these LLMs or roll forward these LLMs to move it forward? And again, also here, lots of the time when we saw before, when you move LLM to LLM, unintentional things start breaking, right? Things that were structured in outcome, but suddenly unstructured in outcome, and you have to really deal with that. So we invested a lot in more A/B testing. So can we actually test more live 2 scenarios with different LLMs? We also, again, really went looking for how to do the tracing better, how do we actually do the telemetry better so that we can understand what's going on. And the last one is we really started working on building our own golden data sets for internal benchmarking so that we don't trust anymore the next new LLM that potentially is better in reasoning, but actually in our scenario might not be better in reasoning. So we built a playbook, and we built a playbook together with some biases Weave, where we really start tackling the 3 things that we think is most important for today for us. So the first one is that we really start capturing much more of the knowledge. So what you saw before, right? Really trying to understand why humans like some things, humans don't like something, really tracing much better what questions are being asked to the system. Do people actually then follow through with the question, or do you actually accept the suggestions, or they don't accept the suggestion, and then try to keep that as a golden data set, right? Once we know this is the type of questions to this type of answers that the end user likes, that we can actually test it in the future. The other one is because now we have the golden data set, we can do much more rapid prototyping. So we can actually take that golden data set, and if there's a new LLM or there's a different type of strategy we want to test, we can actually test that now in our evaluation metrics, right? So we have lots of easy scores. And the last one is we invested in tracing, in monitoring of the product when they go live. So we no longer have a black box running. We actually measure everything that people do so that we can actually try to fix this and things that need it. And one of the big challenges, for example, we have today is around speed. I don't know if people already work with multi-agent systems, but the end user find them very, very slow because every agent you add, every prompt you add adds time. So people start questioning, why is ChatGPT so fast? Well, this enterprise tool takes 20 seconds to answer a very simple question. So we're trying to see how we can do that by memory or caching and things like that. But by tracing it, we at least start understanding when and where things are slow, and we can actually do a much more targeted approach. So how we do it more practically, and I think people can see the slides later as well, right? But we have IGA. IGA is our internally built framework of how we build Gen AI solutions. I guess today you would say agentic solutions. And what we have been doing with weights and biases is really bringing in that core piece in the middle. So we really bring in the evaluation and the tracing inside our framework through weights and biases, while all the other things around it, like this, how we build the tools, is actually a native Microsoft solution. Not sure if this is too helpful, but this is for people to see, right? So if you think about how we do it in a day-to-day life, how my data scientists are using it, is really they use our framework, and because they use the framework out of the box, they get straight away all the tracing from Weave built in, right? So if they build a user interface in one of our tools, there is cookie creating, templating, or there is built-in tracing, so that from day one, everything is traced inside our platform, so that over time we build up this knowledge base of how we use solutions and how we optimize the solutions. That said, I think I also wanted to talk a bit about today on physical AI, which is more our manufacturing space. Is more about how we actually move outside of digital tools into physical tools. And a lot of it is around how we control real-time critical biological processes, so growing cells. So for people that don't know, manufacturing is extremely complex because it's a multi-step process, and things are not that controlled as you might think because it's cells, and cells are living. So things are going through many steps where there's always a lot of opportunity for things to go wrong, right? So when you start with the seed expansion. So these are the first cells that you start to grow. Then you bring them to a bioreactor where you really start to scale up the growing. Then you have to harvest them. Then you have to purify them. Then you bring them to our secondary sites where you start filling them, put them in the packaging boxes, and actually later on ship them to our patients. So it's a multi-step process. It's very complex, and a lot of chances of things going wrong. And of course, given the process is so slow, it's very bad if something goes wrong in the purification step, because then you have to go all the way back to the first thing. So what we've been working on for the last 5 years is digital twins, really trying to build real-time decision-making on these biological processes by adding sensor technology in there, where you start having streaming data from what's going on with your cells. Initially, we were building lots of basic BI predictive models, where you just can say, forecasting, we think the cell's going to do something, so maybe the human operator wants to change something, so that's what we call a digital shadow, where you actually have the model predict a scenario, but the human takes the decision. And we have also some real digital twins where we do it real time. So when we do level 3 digital twin, that's really where we have autonomous decision making, where the sensors are non-stop telling what's going on, predictions are happening, and automation is controlling the process. So it's a simple example, right? Because maybe it's a bit complex for if you've never done it. If you grow vaccines, for example, you actually start very simple with some cells, some base cells, you add some nutrients, and then, of course, you grow this, and at the end, you get the antigen, the product that makes the vaccines. Obviously, there is a lot of variance, and the sources of variance can be from the initial cells. Some cells are happier, some cells are unhappier. It might be temperature, it might be all kinds of things. Sometimes we also see when we change from vendors, from raw materials, the cells respond differently. So we need to control for that. We can control that with a few things. Most often the easy way is controlling the feeding strategy. So when and how you add the feeding, or things like temperature. And then, of course, how long you make them grow, right? Because cells grow is kind of optimal, and stopping at the right time will give you a higher quality antigens versus just running it till the end. So, and then I hope that this works. Yeah, it does work. So, for example, here is a sensor for how we do it for one of our key vaccines. And as you can see, the real-time sensors will actually tell us what's going on in the cells. There is a growth rate, so you can actually see on the left how we start predicting what the cells are doing and if the growth case is good. Based on that, we can actually start predicting the cell density, so how many cells are going to be in our bioreactor at the end. And because of that, we can predict when we should actually stop our manufacturing process. So we went from a very fixed process where you say every batch takes 8 hours or 3 days or 5 days. It becomes now much more like what it might be 3 days and 2 hours, because it looks like that's when the optimal time is for the sensor. And by doing this, we have really now optimized 13 of our key products, really improving yield, but also the quality and the stability of these products. Now, where weights and biases again comes in is, originally we were building everything side by side in a single instance of Azure ML or Databricks ML Flow, but we started having issues getting a unified view of what's happening on all our sites, on all our campuses. So what we're trying to do, TwinOps is our internal built SDK for how we build digital twins. We start integrating both core weights and biases Weave and models to actually start really tracing when we have humans take decisions through Weave. We trace when they actually accept the prediction or not accept the prediction. And in models, we actually keep much more use of the registry so that we really know what model was in production at what site at what time, what was the performance. We can then run retrospective experiments to say, what if we had actually use a different model? Would the experiment maybe be better? And we use that. And then the last thing, and this is actually what I was discussing last night over dinner, we really focus on value dashboards as well. So we would like to actually have a real-time dashboard about how much value each of our AI models are making. So we're trying to use the registry and weights and biases as our core platform, and then on top, we're building dashboards to project how much money we're actually making or how many extra doses we are making by using these type of AI technologies. So that maybe this is a bit the same as before, right? But the reason why we also wanted a unified platform and a single platform is because our ecosystem is extremely complex. We're a very large manufacturing company, so we have a lot of vendors, and we don't always have control about what vendors is picked. So for example, today we have Google Cloud, Microsoft Cloud, we have Databricks, we work with C3, and we work with NVIDIA on the edge. It's extremely hard to get a unified view of what's going on all these platforms. And with now the agentic hype, there's more and more VC startups that we're buying. It's getting worse today to track. So what we're trying to build with weights and biases is a single lens view that we say this is going to be our registry of truth. These are the models that are in production. If we ever get an inspection or an audit, we can say these are the models that we are actually using. They were used then. And it doesn't really matter where the inference is happening. So we kind of decouple that. This is especially important for us is because we are really scaling to thousands and thousands of models. We have some of our forecasting solutions. I think they're running 30,000 machine learning models. So it's very, very hard to do that manual rather than having a centralized registry. Now, another thing what we are working on is actually, I think I saw it earlier today as well, the pins were on the slide as well. It's really these physics-induced neural networks, because a lot of the time, actually, we don't have enough data. You don't run actually enough samples a year or batches a year. And sometimes as well, lots of our data comes from R&D, which is small scale. Well, actually manufacturing, we run big scale. So we're trying to use now what people call physics-informed neural networks to start building machine learning models or neural network models that are based out of the physics space. So we're working together with NVIDIA on that, and that's really to optimize our digital twins where we don't have enough data, where the process is maybe too complex, where today we have process scientists building these machine learning models or these mechanistic models from scratch. This might take 12 months. It's also very hard to fix. If a model doesn't work, you have to go back to the scientist, and the scientist maybe spent another 6-12 months refitting the model. So by working with NVIDIA and working with the PIN libraries, we actually believe that we can build a much more robust framework that actually can much quicker scale from small data to productionized models. And we also believe with these physical induced networks, we can actually move from different constraints, right? So even if you have only training data on a small vessel bioreactor of 8 liters, we might be able to then actually scale it to a 2,000-liter bioreactor, which we know today is extremely hard to do for the machine learning models. So we tested that. This is the first time I show this publicly, so it might be wrong next time that we change it, but we tested on one of our machine learning, or one of our mechanistic models that is actually in production. So that's the blue. These are the traditional way of building machine learning models in that team. And we actually compare it with the mechanistic, or the pin-induced mechanistic model. And as you can see, for the last 5 batches, if we would have run the pin-induced network, we would have had much more performance for my digital twin, right? So we're trying to see now, can we scale this out? Can we actually run a strategy to replace all our existing digital twins with this type of methodology? So it works very well, but it's very complicated. You need to have people that really know equations and to run that. The other thing I want to share a bit is about when we talk about physical AI, real robotics, and vision systems, and how we have been working on that in GSK for a while. So we've been trying this for very long, and not always with success. I'm not sure if the video works, but it's actually in one of our clean rooms. So after COVID, we spent a lot of effort trying to optimize our sites by bringing new types of sensors. So we put in cameras in clean rooms, and we put also actually LiDAR sensors in clean rooms, because we thought if you start measuring, you might be able to predict contamination risk, or when people don't follow the process, or try to start predicting scenarios that are maybe not that easy to find in sensor data, right? You cannot put sensors everywhere. I can tell you, at that time, it was not good enough. So all the skeleton tracking, we couldn't actually get machine learning to predict anything properly. And actually, when we did the LiDAR data, the LiDAR data was actually too noisy to actually get it to work for us, right? But again, maybe today it would be different. It might be much better. But at that time, we couldn't get these models to work in a systematic way. What we do manage to get work is what we call environmental testing. So one of the things we do to make sure that our sites are clean is that we have these Petri dishes all around campuses. We have 3 million of them a year, where we actually measure if the sterile rooms are actually sterile, and that's by just growing them and then actually counting. And obviously, this plate here is really, really bad. People would be very, very unhappy. Normally, these plates are empty, right? So just be clear. This is for you to see bad. This is what we don't want. The process is very human intense, right? Because this is a regulatory space. Normally, it's been counted by 2 humans. So it's not even one person counting them, it's 2 humans counting. And the project that we did is replacing 1 human with AI, and then the other human is still there to validate. And of course, in the future, we would like to go fully autonomous, but that's probably more a regulatory problem than a machine learning problem. And what we learned doing that is actually making these models. It's not that hard anymore, right? As people know, deep learning got pretty good. You can pretty easily count dishes, and you can pretty easily count numbers. What we did see that our MLOps instances were actually not smart enough, right? Because we started encountering, when you roll this out on 9 sites globally, and you have 3 million of these pictures going through your systems, that you start seeing all kinds of outliers that you haven't encountered before that actually break your whole pipeline. So for example, you see here a defect. There were actually vendor defects on the plates that created. The deep learning didn't know what it was, so obviously didn't count it. Well, obviously it should have been counted. The same on the bottom, you see some pictures of when there was actually mold. Again, mold is so big, it takes over the whole plate. We didn't know. Obviously, operators were not happy. And because it was all very much based on a reactive system, right? An operator complaining that the picture was counted wrongly, it took like 5 months for us to build new deep learning models to fix this. So what we've been trying to work on is making things more proactive, right? So if you think about it, the current system, as it is in production today, is very manual. We have 9 sites around the world. The GPUs are there. They count the dishes. It gets stored in a central database. The human validates it. Once a month, there is a business meeting where we give them a PDF. In the business meeting, they just discuss the accuracy. If the accuracy is not good, they tell the development team to build a new model. Then the next meeting, the development team might give an update to the business team to decide if you go to production or not. It's very slow. It's very prone to humans, and it's not very modern in a way. So what we're trying to do with weights and biases, with the registry and with the reporting, is building a much more automated MLOps system. So the idea is if we bring it all to a single platform, we can build agents or machine learning models that actually detect when the data drift or the model drift is happening, so that the development team is already building the model. So by the time you actually report to the business stakeholders that the models don't work, you might already have a solution for them to bring to production. The other benefit is now we can actually give a real-time dashboard or report to our business stakeholders. So instead of them having to wait every month for the PDF to see what's going on, all of our site directors can actually go into the report to see exactly how many plates have been counted, what the accuracy was for each day, and if they still like it or not. So we have a much more end-to-end closed system because of that. And then the last thing where we're really working on, and this is very much where I spend most of my time on actually, is thinking about how we start bringing in humanoids in this system. So as you can imagine, we have a lot of manual activities happening on site, and as you saw with the visual inspections, but also with other activities. So we're really trying to understand how can we bring these vision language models or these vision language action models into a manufacturing site like us. How do you actually get these models robust enough? And how do you actually get then at some point approvals from regulatory bodies as well that you actually can do that? And this is again where the experimentation part of the model part from weights and biases comes in, because we really need to make sure that we can prove that there is zero negatives. There cannot be false negatives. Because in our industry, if there's a false negative, you might actually ship a product to a patient that puts them at risk. So it's a very difficult game, because there is no longer a human potentially that's accountable for that mistake. It becomes a machine. So with that said, thank you for your time, and mainly also thank you. I don't know if people from my team are here, but they do the work.